Okay, take it away.
Hello, my name is Ulrik, and I'll be talking about this DSL that we developed that uses a generate and test paradigm to construct quantum circuits. So generate and test is an idea from classical programming where a naive implementation would generate all possible solutions, then apply some function to all of those solutions and filter those to find the best solution. And we've designed this DSL that, using the same idea, shows that you can use the same underlying classical intuition to understand various common quantum algorithms. So the snippet here is not in the DSL. That's just pseudocode or Haskell to kind of show the idea here. So this is roughly implementing Shor's algorithm to factor the number 15. What you want to do is you generate all possible inputs x, you apply some function, in this case it's a modular exponentiation function, and then you filter the results so that you only get inputs consistent with a particular output. And then the only quantum magic here is this quantum Fourier transform that you apply at the end, and that allows you to then find the period. But our goal is to kind of abstract that away so that you only have to think about these classical steps. So in our DSL, this is all you need to implement the Bernstein-Vazirani algorithm. I'll go through the details, but for now the important part to note is that the oracle function is implemented as an entirely classical Haskell code for a bitwise dot product, and that's annotated with this build oracle keyword to construct a circuit from it. And then to specify the full program, you need three things. You need to specify how many bits are in the input, you need to specify the oracle function from above, and then you need to specify which query you want to apply. So I'm sure most of you are familiar with these algorithms, but these are the four algorithms that we focus on. They are algorithms where there is a known polynomial or exponential speed up over the best, or in the case of Shor's algorithms, the best known classical algorithms. And they all share this property where you're querying some property of an oracle function. So for Deutsch-Josa, you're querying whether the function is constant or balanced. For Bernstein-Vazirani, you are finding the secret bit string where the oracle function is this dot product that we had before. And then for Simon's algorithm, Shor's algorithm, you're finding some kind of period of the oracle function. Now, all of these algorithms have the same structure, and this corresponds nicely to what we saw with the classical generate and test paradigm. So you generate a superposition of all possible inputs, you apply your oracle function, you measure the output register, and this has the effect of filtering your superposition to only get those that are consistent with the measurement result. And then there's this quantum Fourier transform, or for some algorithms, it's an approximate QFT, which is just a Hadamard transform. So the only difference between these algorithms is in the choice of the QFT, whether it's a full QFT or the approximate QFT, and then the initialization of the output register. And so in our DSL, the programmer gets control over this by selecting a query type. So currently we have three implemented. Period and bitwise period are respectively for Shor's and Simon's algorithms, which only differ in whether they do the full QFT or the approximate QFT. And then the other two algorithms, when you think about it, what you're querying is in fact a subset of the Fourier coefficients of the Fourier expansion for the oracle function. Specifically, the subset where that set S here is, corresponds to singleton sets. And in this case, in both cases, you're using the approximate QFT and setting up the output register to get phase kickback. So our solution is built on Quipper, which, as many of you probably know, is a quantum programming language embedded in Haskell. The points I want to point out here are that it uses the circ monad to capture the effect of building circuits, and then it distinguishes between values that are available only at, or that are available at circuit construction time. These can only be classical, and so they're called classical parameters. And then the values that are available only at circuit execution time are called inputs. They can be classical or quantum. And so you have these families of types. So for Booleans, you have bool, bit, and qubit. And then it also provides other families. For example, for fixed length integers operating mod 2 to the n, you have int m, cint, and qdint. And then Quipper provides this circuit lifting functionality, so you can write classical Haskell code and annotate it with this build circuit keyword, and that automatically builds a circuit for you. So this is a slightly modified version of the Bernstein-Vazirani example that I had before. And the build circuit keyword makes that this, in addition to declaring the classical function dot, it also creates this circuit called template dot, where you'll note that all the bools have been replaced by qubits. So it's a useful, although not entirely accurate, mental model to say that classical parameters in this code gets replaced by the corresponding quantum input types. However, you don't always want all your classical parameters to be replaced. For example, for this oracle function, the secret bit string should still be a classical parameter. So Quipper provides some support specifically for bools. They have an ad hoc solution for marking some of them as bool params that are not lifted to qubits. But we developed a more general solution that works for any type. So we have this paramonad. Not shown here are all the type class instances that you'd expect for an identity monad. And it has this family of lift p functions, which in classical code are just equivalent to the lift m family. But within the DSL, they should be considered keywords, because when you prefix a term with one of these lift p functions, then that disables lifting that term into a circuit. And then on top of this, our DSL provides this build oracle, which does the same thing as build circuit, but it also creates this instance of the oracle type, which just encapsulates the classical function together with the quantum circuit, which is important so that we can either simulate it classically or run it as a circuit. And has the supply param function, which is just function application, and also access the introduction form for the paramonad. And then, as we've seen before, the final program just specifies these three things. So for a more complete example, here's Shor's algorithm, specifically for factoring now, and then I guess this is the period finding subroutine of it. So you would build a function to find to do modular multiplication, which is the obvious implementation. Then you can use that to build one that does modular exponentiation. It calculates here a to the x mod n. The details aren't really that important. In this case, it's treating the exponent as a bit string and effectively doing exponentiation by squares. And then your full program is specified like this. You say how many bits your inputs are. You have your oracle function, apply the parameters to it, and then say you want the period. So our DSL, we have an implementation that can convert these programs into Quipper circuits, and we've tested all four of the algorithms that I mentioned before. just via simulation. I gave some qubit and gate counts here. You'll note that they are quite high. So using the Bernstein-Vazirani algorithm with 4 bits requires 18 qubits and 34 gates, and then Shor's algorithm, just a factor 15, requires almost 400 qubits and 60,000 gates. However, there's still some obvious opportunities for optimization here. Here I'm showing the circuit generated for the Bernstein-Vazirani algorithm. And you'll note that these 3 ancilla qubits are effectively useless. They are initialized to classical values and just used to access those constants. So the one is just 0, and then 2 of them are initialized to the secret bit string. And so the missed opportunity here is that with our annotations of this paramonad, you know which operands of an operator have a effectively a constant value when the circuit is constructed. And so using that, it should be possible to automatically select more optimized implementations of the operations. And I believe that this is also the largest problem with the Shor's algorithm example, which is using a naive implementation of multiplication, which assumes that both inputs are quantum values. And so yeah, this project is a work in progress. As I said, there's still some obvious optimizations to do. We'd like to identify other common idioms from other algorithms that we can implement. An obvious example is Grover's algorithm, which is also definitely something which queries a particular property of an oracle function, and it would be pretty straightforward to add to the DSL as well. And then there's still some implementation work to be done, like the classical simulation without building a circuit first, and post-processing for some of these algorithms. So just to summarize, our first contribution here was the extension of Kuiper with this scheme to distinguish these classical values that we do want to be lifted into quantum types from those that we don't. Then we implemented this DSL that allows one to write quantum programs for specific algorithms by only implementing a classical oracle function and specifying what query to perform. And then we believe that this demonstrates that there's a certain classical intuition that is in fact sufficient to express some common quantum algorithms. I want to thank Amir Sabri, who's guided me throughout this project. The source code is available there. You may want to wait until tonight so that I can just go and get a nice README ready. Thanks for your attention.
Thank you, Ulrik. I'm awaiting that README so I can download this and play with it. Questions?
So the paradigms generate and test is less general than just having oracles. A lot of algorithms which use oracles which are not of this form. So what's the prospects of extending this to a bigger class of things?
So we have some ideas. Nothing very concrete yet. And now that you mention it, maybe if we do end up extending it in that way, the name is no longer that appropriate. But so we have some ideas that you can find other algorithms that would kind of fit the same pattern, and perhaps prove that there are larger classes of algorithms that do it by so if we look at, let's say, decompositions of algorithms into Toffleys and Hadamard's and rotations, then if you can find some circuit identities that effectively allow you to commute things, doesn't have to be a plain commutation, they could change phases and stuff, but so that you can kind of get things into the same form where you have, say, Hadamard's on the one side and Hadamard's or a QFT on the other side. I think that's a promising direction that I'd like to look into.
So you mentioned that the circuits generated are often very inefficient. They have a lot of extra qubits. There are many people in this audience who have existing circuit optimizers. Have you tried just throwing the output circuits into any of these and seeing if it sort of solves the problem?
Not yet, but that's a very good idea.
All right.
Yeah, I think, as I said, some of it is very obvious inefficiencies, like those extra ancilla qubits that it allocates and just gives them a constant value. So I think a lot of optimizers will probably be able to do a good job with those, but I haven't tried anything.
Yeah, it's a good question
concretely.
because some of them don't do the naive stuff, they only do the smart stuff. So I found that it's not always, like sometimes there's this really obvious opportunities for optimization that they don't get. So it would be an interesting study. Any other questions? All right, let's thank Ulrik again.